for the week. So here we go. 5-3.
5-2 was hard.
5-2 was hard. Those antiderivatives and stuff. Yes. Got to take the derivative or the antiderivative. All right. So for 5-3, what we're going to do here is we're going to have f prime and f double prime graphs. And this is going to get a little tricky too. Chapter 5 is tricky. Okay. So we're going to talk about the first part, which this is a little bit of review, but it's good review because 5-2 was tough. This is called the first derivative test. First derivative test for Extrema. Okay, we're going to draw a real funky graph. It's pretty cool though. So go ahead and draw like almost like an x-axis at the bottom. And on here, we're going to have an interval from A to B. And it's going to be a closed interval. All right, so we're going to draw this. We're going to start, I don't know, let's start way down here like this. And this is what we're going to do. We're going to like slope it up and then keep going. Go to a peak. No, it's going to be a weird one. And go to like a cusp up here and then come back down to here. There you go. Try to draw that as best you can. It's pretty gross. This is supposed to be a little bit smoother in here. Okay? So there you go. There's the graph. And then some of these points are important. Okay. So let's talk about this right here. This we'll call C1. It's not a minimum though. It keeps increasing in here. I know that I didn't really draw it very well, but you can kind of think of it as like a cubic in there. But at that point right here, at this point, f prime is equal to 0. Okay? All right, this other point, so that was C1. Let me relabel this green. C1. This point right here is important. That's a peak, reaches the top. And that we'll call C2. And we know that that is where f prime is also equal to 0. Okay. We also have this point right here.
Wait, what about the other one?
Which one?
To the left of
The blue?
right, like above your pencil. That looks like it's a maximum, but it probably isn't.
No, yeah, I didn't draw it very well. So this red one we'll call C3. And then that is also where f prime equals 0. And then we have this point up here. We'll call that C4. And this yellow one is where f prime is undefined. Okay? And then we have B. That's 4. C4. C4. Okay, so let's talk about all of these things in here. This right here, this interval, this is where f prime is greater than 0. Our function is increasing. So f prime is greater than 0. On the left side of this green, in between the green and the blue, same thing. F prime is greater than 0 in here. It's still increasing, our function is. From the green to the red, that is where f prime is less than 0. Our function is decreasing. From the red to the yellow, that's where f prime is positive again. Our function is increasing. And then from the yellow to B, f prime is less than 0. Now, let's talk about all of these critical points, okay? So we have critical points and we also have endpoints. We did this in 5.1. Critical points and endpoints. And let's say what all of these are, okay? So our endpoints, of course, are A and B. And on this graph, A is what we would call a what? On my graph, it's the perfect, absolute minimum. Okay? I don't know if you drew it that same way, but nobody else is below it. See, things are pretty close to it, but I wanted it to be the absolute minimum. And then B is what? B is a minimum, but you could just call it a local minimum or relative minimum. You could just call it whatever. I would probably just say local min. It's a minimum in its own neighborhood, but it's not the minimum of the graph. Okay, our critical points are all the C's there. So let's talk about these. All right, C1 is where f prime is equal to 0, but it's not an extreme value. It's not an extreme point. It's not a maximum or a minimum because it keeps increasing.
Why is it a critical point?
It's a critical point because the derivative equals 0 there.
How do you know that?
Because the tangent line is horizontal. Slope, exactly. All right, C2 is also where f prime equals 0. We said that. That is a local maximum. Local max. C3 is where the derivative equals 0. That one, it looks like that's the, for me, is that the absolute min? No. It's just a local. Yeah, A was.
So are there only critical points when the derivative is equal to 0?
Not quite, because then C4 is where a derivative is undefined,
It's absolute max.
and that's the absolute max of the graph. So our minimums and maximums occur at the endpoints, and then at our critical points, which is either derivative 0 or derivative is undefined. But if it's derivative 0, it doesn't mean that it's a maximum or a minimum necessarily, as we found out. Okay? So let's talk about that. That brings us to theorem number 4. What were 1, 2, and 3? I don't know. Thank you.
Mean value.
Mean value theorem, yes. All right, this is theorem 4. This theorem is going to be nice. You're going to like this one. It's pretty easy. It says if f prime, if the derivative changes signs from positive to negative at C. From positive to negative at C, some point, some x value C, okay? Then f, the original function, has a local max at C. It could be the absolute max, it doesn't matter, because absolute maximums are also local maximums too. But if f prime changes signs from positive to negative at C, then f has a local max. So let me show you. It's like this. Bless you. Let's say here's C, okay? And let's say we have some kind of a parabola or something. F prime on this side is positive. F prime on this side is negative. So if it changes from positive to negative, then that would be a maximum, right? We talked about that already. On the left side, if it's positive, on the right side, if it's negative, it's a maximum. Even if you have some weird graph like this, right? That's C. On the left, f prime is positive, and on the right, f prime is negative. C is a maximum. Okay, it's a local max. It's any max. It could be an absolute max, but it's for sure a local max. That's what the theorem says. And then the theorem has the other one that says if it's negative on the left and positive on the right, then it's a local min. Yes. Okay, so it has both. All right, so we're going to do some more of these. Number 1. Rip it. All right. Okay, so this is what your directions are going to be. It's going to say to use the first derivative test. So we know we're going to have to take the derivative to determine, and this is really review. We've done these in 5.1 and 5.2. Determine local extreme values. First derivative test. Okay, the first derivative test is going to be to take the derivative, set it equal to 0 or undefined, and then we have to test the intervals for positive or negative, see if it's increasing or decreasing, then we'll determine local or maximum minimums. It's the same thing that we've done before. It's without your calculator. There's no calculator on this whole lesson, 5.3, okay? All right, so here we go. Y equals negative 2x cubed plus 6x squared minus 3. Okay, so here's our function, and we're going to take the derivative of that, and we're going to set it equal to 0. It's a polynomial, so you know there's no undefined parts in a polynomial. So here we go. Take the derivative. You get negative 6x squared plus 12x. Set that equal to 0 and solve. So we have a quadratic that we're solving, which can be a little tricky. We're going to factor this. We can factor out a negative 6x. You factor out a negative 6x, you're left with x minus 2 equals 0, and then we solve. So where this would be 0 would be at 0 and positive 2. Okay? All right, so now here comes our chart that we're going to make. I like to make a number line. Here's 0 and here's 2. And we're going to use the first derivative test to test these out. So when let's go over here to negative infinity to 0, and we're going to pick a point. We're going to pick something like x equals negative 1. We're going to plug it into the derivative. We're testing the derivative. That's why it's called the first derivative test. So you take negative 1 and you plug it in for y prime, which would be negative 6 times 1 plus 12 times negative 1. And what do we get there? We get a negative. Okay? All right, let's pick a number from 0 to 2. 1. Plug in 1 into the derivative test, to test it. You get positive. And then I would probably pick x is 3. Plug 3 in, you get negative 6 times 3 squared, 9, so that's going to be negative also.
What if it's like negative, positive, positive?
Ooh, it can. Those are the ones that are going to bounce, you know, like they're squared. They have a whole thing squared. Yeah, we'll do that too. This is like a normal one.
We've had that in our other room.
Yes, yeah. All right, so let's talk about these real quick. So this one is going from negative to positive back to negative. So if this is a negative, that means our function is decreasing and then it's increasing. So x equals 0 is going to be a minimum. Okay? Over here, it's positive on the left and negative on the right. That means it's increasing. So x equals 2 would be a maximum. And then you can go ahead, and they might want points. So you'd have to go back to the original function, and you'd plug 0 in, you get negative 3. And you plug positive 2 in. That's a little tough to do without your calculator. You get positive 5. So that's a min, and that's a max. And this is really cool. Back in the olden days, when they didn't have graphing calculators, because you could find the zeros and then you could actually graph these really easily. So you'd go to 0, -3, and you'd go to, what was the other point? 2, 5. And then you can graph this. You know, it's decreasing here, increasing here, and then decreasing there, and you graph your cubic function. It's pretty good without a calculator, using calculus. Pretty amazing, huh? Yeah, you're so stoked on that one. All right, now, that shouldn't have felt new, because it really wasn't new. We've done that kind of stuff before. Now let's talk about the second derivative test. We're going to talk about concavity. Had a bunch of concavities, yeah. Got them all filled. Mouth's all fresh and clean. Okay, concavities. Now, if something looks like this, we call that concave up. And if it looks like that, you're right, concave down. Okay, so how do we check for concavity? Well, you do that by finding the second derivative. So, if f double prime is positive, then your graph will be concave up. The second derivative. And if f double prime is negative, less than 0, then of course it's concave down. And I could have done that on that last one, checked for concavity, but I knew that it was a negative x cubed, and you guys know from Ham and Ram we did the leading coefficient test, which tells you how to graph. Hopefully you remembered that. Okay, are you ready? Let's do one of these. Number 2. All right, this one's tough. Suppose that y equals negative x to the 4th plus 4x to the 3rd minus 4x plus 1. And it says here to use the concavity test to determine where this graph is concave up and concave down. Okay? Yes. Concave up, concave down. So we're looking for intervals. Okay. All right, you ready to take the derivative twice? Let's do it. All right, so the first derivative would be negative 4x cubed plus 12x squared minus 4. Okay. And then the second derivative would be negative 12x squared plus 24x. All right, so what you want to do is you want to set that equal to 0 so that you can find kind of like, your critical points here. That's going to split up your into your intervals. So set it equal to 0 and solve. Once again, we have a quadratic to solve, so let's go ahead and factor out a negative 12x. Hey, it's the same ones, isn't it? That's funny. I didn't mean to do that. So you get x minus 2. And so we get x is 0, positive 2. Okay? It's kind of like doing that first derivative test. You find the zeros, and then that'll break it up into positives and negatives. This is going to break it up into positives and negatives too, but it's going to tell you if it's concave up or concave down instead of increasing and decreasing. Increasing and decreasing is first derivative. All right, so we have 0 and 2. Now, you're testing f double prime. Not f prime and not f. You're testing f double prime. So let's plug in x equals negative 1 into the second derivative. And it doesn't matter where you plug it in. If you want to plug it in here or down here, it really doesn't matter. So you take it, plug it in. I would probably plug it in here, and I get negative 12 times negative 1 is 12. 1 minus 2 is -1, so I get a negative here. From 0 to 2, it's x equals 1. It's a good number to choose. Plug it into here, you get a negative times a negative, which is a positive. You don't care what the number is, you're just checking for the sign. And then I would probably plug in x is 3 again. I would get a negative times a positive, which is a negative. All right, so I would say that this graph is concave down from -infinity to 0, and then also from 2 to infinity.
You don't put a bracket on the 0?
They don't want brackets, no. That point we're going to talk about 0 and 2. I know, for the increasing and decreasing, they included that, but I don't include them ever. I leave them off.
I only include them because you said to.
I know, but but that's because the book does.
But for the concave and stuff, they don't want.
They don't. Those points are going to be special, and we're going to talk about that tomorrow. Okay, and then concave up is going to be from 0 to 2.
We won't get marked off.
No, if you bracket it, that's fine. Yeah, it really depends on your professor too that you'll get in college.
Are you gonna want us to graph it, Michaela?
No, I was just going to show you. Like, what's happening here, it's a 4th degree polynomial, so it's going to look something like that because it's pointing down. And do you see how that's going to have 2 parts that are concave down? That's those 2 there. And then 1 that is concave up. That's not the graph of it. It's just an idea of what's going on.